Today we're going to have a look at rates of reactions. Now, the rate of a reaction is a measure of how fast a chemical reaction happens. It can be measured as a change in the concentration or amount of reactants or products per unit time. So in simple terms, it tells you how quickly the reactants are used up or how quickly products are formed. Now, this is of economic interest, as if we have a higher rate of reaction, it implies that a higher rate of production and hence more efficient and sustainable process can be attained. Now, the rate of reaction can be affected by a few conditions. Firstly, the concentration of the reactants, the pressure, especially in gases, the surface area of solid reactants, the temperature of the reaction, and the presence of a catalyst. Now, before we go into these conditions, we need to understand the collision theory. Now, the collision theory is a model in chemistry that explains how chemical reactions occur and why reaction rates differ for different reactions. Now, in order for a reaction to occur, certain conditions must be met. Firstly, the particles must collide. So for a chemical reaction to happen, the reaction particles, the atoms, the ions, or the molecules must collide with each other. Secondly, sufficient energy or activation energy is needed. So the particles must have enough kinetic energy to overcome the activation energy barrier. This is the minimum energy needed for a reaction to occur. If they collide with less than this energy, then no action will happen. But if they collide with enough or more energy, the reaction will happen. Lastly, the proper orientation is needed. So the particles must collide in the correct orientation for bonds to break and new bonds to form. Not all collisions lead to reactions, only the ones with the right alignment do. So to sum it up, if particles do not collide with each other, or the collision doesn't have sufficient energy or is in the wrong orientation, the reaction will not occur. All three of these must be met for the reaction to occur. So how do we increase the number of successful collisions? Firstly, we can increase the number of particles per unit volume. So the more particles in a given volume, the more frequent and successful collisions there will be. Secondly, we can increase the frequency of the collisions. So if there's a greater number of collisions per second, this will give us a greater number of successful collisions per second. We can then also increase the kinetic energy of the particles. So if we have a greater kinetic energy, this will mean a greater proportion of collisions will have an energy that exceeds the activation energy, and the more frequent the collisions will be as the particles are moving quicker. Therefore, more collisions will be successful. Lastly, we can decrease the activation energy. If there are more collisions that exceeds the activation energy, there will be more successful collisions. Now, the first way that we said we can increase the rate of a reaction is through concentration. Now, if we draw a graph of the total mass or volume of a product that's formed over time, a low concentration of reactants will give us a graph like this, where products are steadily formed over a period of time until it reaches a maximum product. But if we increase the concentration, our graph will have a steeper gradient at the start. It will become horizontal sooner, but it will form the same amount of product. This will show that increasing the concentration increases the rate of the reaction. We can explain this in terms of the collision theory as well. Let's say we have a low concentration of reactants. They will move around randomly and bump into each other, but the chance of a collision is lower. If we now increase the concentration of reactants, there's more reactants per unit volume, so the chances of them bumping into each other is greater, and the chance of a collision is greater. By increasing the concentration of a solution, it increases the rate of the reaction. This is because by increasing the concentration, there will be more reactant particles in a given volume. This will cause more collisions per second, leading to more frequent and successful collisions per second, and therefore the rate of the reaction will increase. So if we double the number of particles, we will double the number of collisions per second. So the number of collisions is proportional to the number of particles present. The second condition that we can change to increase the rate of the reaction is pressure. Now here we can also show it through the use of a graph of the total mass of product being formed over the time of the reaction. If we have a low pressure, the amount of product being formed will be constant and slow until a maximum is reached. But if we increase the pressure, the graph will have a steeper gradient at the start. It will become horizontal sooner, but again, it will form the same amount of product. So this shows that increasing the pressure increases the rate of the reaction. Let's see if we can explain it using the collision theory. So if we have a certain amount of volume and a certain amount of particles, we have a constant pressure. The particles will move around, but there's a lot of space to move around, so there won't be that many collisions. But if we decrease the volume, meaning we increase the pressure, there will be more particles per unit volume. So the particles will have a greater chance of colliding with each other, increasing the rate of the reaction. So increasing the pressure will increase the rate of the reaction. This is because by increasing the pressure will mean that there are the same number of reactant particles but in a smaller volume. This will cause more collisions per second, leading to more frequent and successful collisions per second, and therefore the rate of the reaction will increase. We then have surface area. Now when we draw the graph of the total mass being produced over time, if we have a small surface area, meaning a big lump of reactant, our reaction will be slow and constant, reaching a maximum of product formed. But if we increase the surface area by maybe breaking up this lump into smaller bits, then it will have a steeper gradient at the start, it will become horizontal sooner, and it will form the same amount of product, just like in concentration and pressure. So this shows us that increasing the surface area increases the rate of the reaction. We can also describe it as when we increase the surface area, we decrease the particle size. Now, what is surface area? Let's imagine that we have a cube of reactant. This reactant is 10 centimeters by 10 centimeters by 10 centimeters. This means that we can work out the surface area by working out the area of each side. This will give us a total of 600 centimeters squared. Now, if we had to work out the volume of this cube, we can multiply the length by the width by the height, and this will give us 1,000 centimeters cubed. Now, if we take the same cube and we cut it up into 8 pieces, which will have dimensions of 5 centimeters by 5 centimeters by 5 centimeters, this means we'll have the exact same volume of 1,000 centimeters cubed, but our surface area would increase to 1,200 centimeters squared. So now you can see that we have the same amount of particles, but the surface area is just greater. So if we look at a particle that has a great surface area, the particles will be able to collide with this particle, but it will only chip away bits and pieces as it reacts. But if we increase the surface area, there's more surface area for the other particles to interact with, increasing the rate of the reaction. This means that increasing the surface area increases the rate of the reaction. This is because increasing the surface area means that we have a greater surface area of particles that will be exposed to other reactants. This causes more collisions per second, leading to more frequent and successful collisions per second. Therefore, the rate of the reaction will increase. Now, if we double the surface area, we will double the number of collisions per second, doubling the rate of the reaction. We can also increase the rate of a reaction by changing the temperature. Now let's refer back to our graph of the mass produced over time. Now, if we have a low temperature, again, our reaction will be slow but constant, increasing up to a maximum. But when we increase the temperature using a higher temperature, our graph will have steeper gradient at the start. It will become horizontal sooner, but again, it will form the same amount of product. This shows that increasing the temperature increases the rate of the reaction. Now, when we use a low temperature, our particles will move slower. They will also have less energy, which means that there would be less successful collisions. But if we increase the temperature, we increase our kinetic energy and our particles move faster. Our particles also have more energy, meaning that we'll have more successful collisions. This is because increasing the temperature means that the particles will have more kinetic energy. This will cause more collisions per second, leading to more frequent and successful collisions per second, and a greater rate of reaction. The effect that temperature has on collisions is not so straightforward as concentration or surface area. So a small increase in temperature will cause a large increase in rate. For aqueous and gas system, a rough rule of thumb is that for every 10 degrees Celsius increase in temperature, the rate of the reaction approximately doubles as well. The last factor that we can change to change the rate of the reaction is by using a catalyst. Now, catalysts are substances which speed up the rate of a reaction without themselves being altered or consumed in the reaction. So if we look at the graph of mass over time again, we can see without a catalyst that the reaction would be slow but constant until a maximum is reached. When we add a catalyst, our gradient at the start would be steeper, the graph will become, but the same amount of product will be formed. So this shows that with a catalyst, the rate of the reaction will increase. Now, different processes require different types of catalysts, but they all work on the same principle. A catalyst provides a different reaction pathway that has a lower activation energy. So this means a higher proportion of the reactant particles have energy that's greater than the activation energy and will result in more successful collisions per second. So when we look at a graph of potential energy over reaction for a reaction without a catalyst, we can see that our reactants have a high energy, we then have a high activation energy, and our product has less energy. When we add a catalyst, our reactant's potential energy stays the same, but the activation energy lowers because of the different reaction pathway that's given by the catalyst. The product's energy also stays the same. So to sum it all up, a catalyst will decrease the activation energy, which means that more particles have a sufficient amount of energy to overcome the activation energy. This means that there's more successful collisions and there's an increase in the rate of the reaction.